Yes. So welcome everybody. It's a great pleasure to have today Alexey Pokrovskiy. So Alexey is a good friend and my frequent collaborator, and he has some exciting results to tell us about random Hall-Paige conjecture. I will just remark that this is a last talk of the seminar in this semester, so hope you enjoy it. Please, Alexey.
Thank you, Benny. Thanks so much for the invitation. Thank you all for coming. So I want to tell you about some joint work with Alp Müyesser, who's also at University College London. So this project is about kind of a big work we have with Alp to apply tools from extremal and probabilistic combinatorics to problems in finite group theory. So the Hall-Paige conjecture is a problem from finite group theory, which was eventually solved using the classification of finite simple groups. And our starting point with Alp was to try and get an alternative proof to this conjecture using tools from combinatorics. And the purpose of this was to apply the tools we developed to other problems in group theory. So I'm going to start by telling you about what the Hall-Paige conjecture is, then go on to what the theorem we proved was, and then talk about some applications. So I'll start by explaining what the Hall-Paige conjecture is. So the first few slides will just be pure group theory. So it's about multiplication tables of groups. So here I've drawn to 3 multiplication tables of groups. They're the addition tables of Z2, Z3, and Z4 modulo n. And the structures that Hall and Page were interested in were transversals and multiplication tables, where transversal, it's a set of n entries in an n by n multiplication table, like the ones I've highlighted here, with the property that they don't share rows, they don't share columns, they don't share symbols. So you have all the different numbers, 0, 1, and 2. So there I've drawn one transversal. The other 2 multiplication tables do not have transversals. So for example, in Z2, this is really easy to see. If you say take this 0, the 1 only occurs in the same row or column, so you can't have a transversal. In Z4, it's harder to see that there's no transversal, and we'll actually see that there isn't one as a consequence of a general principle in a couple of slides. So Hall and Page were interested in the question, characterize all groups which have transversals in the multiplication table. And they actually made a conjecture about what the characterization should be. So this is the conjecture. This is the Hall-Paige conjecture. They said that there is a transversal if and only if a certain group theoretic property holds, which I've highlighted there. I'm going to call this the Hall-Paige property. So let me explain to you what everything in this expression means. So first, on the left-hand side here, what this means is the product over all elements of the group. So you take all the elements in the group and you multiply them together. So let me demonstrate this on the 3 groups you have here. So in Z2, you have 0 plus 1. That's like the product of all the elements of the group, because the group operation is addition. Here you get 1. In Z3, 0 plus 1 plus 2. This is equal to 3, but in the group, because 3 is equal to 0 in the group, because you go in mod 3, that's 0. And in Z4, you have 0 plus 1 plus 2 plus 3, which is 6, which is 2 in the group. Okay, so that's what it means for the product of all the elements of the group. So you might think that I'm being a little bit imprecise about how, with this notation, and that, okay, in the groups I have here, they're abelian groups, so it doesn't matter what order you multiply things in, but in a non-abelian group, you should be more precise about what order you multiply things in here. And I'll answer that in about 2 slides time. Okay, let's now look at what this commutator means. So this means the commutator subgroup of a group. So you might remember this from undergraduate group theory. So it's defined like this. The commutator subgroup of a group, it's the subgroup generated by all elements like this. So you look at all elements in the group, which are the form G times H times G inverse times H inverse. And then you take the subgroup generated by that. So you multiply all such elements together until you stop getting new elements. And that's the commutator subgroup of a group. Let's figure this out for the 3 groups we're looking at as examples. So there are abelian groups, and for abelian groups, so if G is abelian, then the commutator subgroup of the group is just equal to the identity by itself. So I'm using 0 for the identity. So it's just 0 by itself. That's really easy to see because if you have an abelian group, then all these elements, G, H, G inverse, H inverse, because you can rearrange things, they just end up being 0. Okay. So for abelian groups, you're trying to understand whether the product of all the elements of the group is just equal to the identity or not. So let's look at the 3 examples. So here, this is not equal to the identity. It's 1, so it's not in the commutator subgroup of the group. In Z3, this is equal to 0, so it is in the commutator subgroup of G. And in Z4, it's 2, which is not in the commutator subgroup of G. So in other words, Z2 and Z4 do not satisfy the Hall-Paige condition. Z3 does. And notice that matches up with where you have transversals and where you don't. So in Z3, we had a transversal, and the other 2 we did not. Okay, so that's a kind of an illustration of the Hall-Paige conjecture. And Hall-Paige conjecture, this was a necessary and sufficient condition for having a transversal. So they proved one direction of this. They proved the forward direction, and also they proved the conjecture for some special cases. Let me illustrate to you the forward direction. So I'll prove this direction to give you any idea where this condition really comes from, because I think it's a bit mysterious at first glance. So to prove this forward direction, I'm going to need 2 facts about the commutator subgroup, which hopefully you would have seen in, again, undergraduate group theory. The first one is that the commutator subgroup is a normal subgroup of the group. And secondly, so if it's a normal subgroup, you can quotient by it. The second property is when you quotient by the commutator subgroup, you get an abelian group. It's actually called the abelianization of G. So just using these 2 facts, I'll prove the forward direction of the Hall-Paige conjecture. So we need to show that if you have a transversal of a group, then this weird condition holds. So we're given a transversal of the group. So how will I think of a transversal? I think of it as a collection of triples of elements, where each triple is a row, R1, a column, C1, and a symbol in that row and column, S1. So there'll be n triples like this, and that's the rows and columns and symbols of all the entries in the transversal, Sn. Okay, so next I'm going to use the fact that these things live in the multiplication table, which means that certain equations have to be true in the group. So for example, because R1 and C1 has the symbol S1 in it, we get that R1 times C1 is equal to S1. And similarly, you get that since the Rnth column and the Cnth column have the symbol S in them in the multiplication table, that tells you that Rn times Cn is Sn in the group. So we get these equations. Next, I'm going to rearrange things into one big equation, and that big equation will be the following one. So R1 times C1 times S1 inverse times up until Rn times Cn times Sn inverse is equal to the identity E. So what happened here is I moved the S's to the left-hand side of the equations on the previous row, and then I multiplied everything together. Okay, so we have this equation. Next, I'm going to use the first property of the commutator on the previous slide, that it's a normal subgroup. So what do normal subgroups do? You can quotient, and when you quotient, you can get a quotient homomorphism, which goes from the group to the quotient group. So this phi, it's a quotient homomorphism from G to G divided by com G. So this is a homomorphism. Let me now, in this equation, take phi, the phi image of both sides. So when you take the left-hand side, you'll get phi of R1 times phi of C1 times phi of S1 inverse times all the way up until phi of Rn, phi of Cn, phi of Sn inverse equals phi of E. So all that happened here is I took the phi image of both sides, then I used that phi as a homomorphism. So on the left-hand side, you could distribute it through the multiplication. And also because it's a homomorphism, phi of E is equal to E. Okay, so now this is another true equation, and this is an equation in the quotient group, G divided by commutator G. So now we'll use the second fact that the quotient group is abelian. So that means that I can rearrange this equation however I like and still get another true equation. And the way I rearrange it is, let's group the R's together. So the product of the phi of the Ri's times, let's group the C's together, the product of the phi of the Ci's, times, let's group the S's together, the phi of the Si's, and let's put the inverse outside here. So this is equal to the previous line. Okay, now let's again go back to the fact that this came from a transversal. So what does that mean? So in a transversal, you have one symbol in every row. So these Ri's are actually just some permutation of all the group elements. So I can rewrite the first product as the product of phi of G, where you range over the elements of the group. The second product, again, because the columns are just all the group elements under some permutation, is the same thing. And the third product, similarly, because the symbols are all the symbols in the group, it's equal to the same thing. Except now you have an inverse here. Okay, now you have a cancellation, don't you? So this cancels with this. And you're left with just the first term. And let me again use the fact that you're a homomorphism to take the phi outside of the product now. And we now have our product over all the elements of the group elements appearing. So what do we know is that phi maps this to the identity. So now we're done, basically, because let's think about what does it mean for phi to map something to identity. Phi is a quotient map. So it maps something to the identity if and only if the thing that you're mapping, so the thing inside the brackets here, is inside the thing you're quotienting by. So this last line happens if and only if the thing inside the brackets, the product of all the elements of the group, is inside the thing you're quotienting by, which is the commutator subgroup. And look, we've exactly proved what we wanted. So this is what we wanted to obtain. Okay, so hopefully this gives you an idea for where this Hall-Paige condition comes from. And also hopefully it gives you an idea why I'm not being precise about what order you multiply things in here, because if you look at kind of these middle few steps around here, so they took place in the quotient group. So therefore, because the quotient group is abelian, I was able to rearrange things however I like there. So basically, like if you wanted the precise version of this conjecture is that there is a transversal if and only if for every single possible way in which you rearrange the elements of G, you end up in the commutator of the group. Okay, so that's a conjecture. As I mentioned, Hall and Page, they proved the forward direction, and they also proved it for some special cases. Then by now, the conjecture has been proven in full. So this was done in a combination of works by a combination of 3 papers by Wilcox, Evans, and Bray. So Wilcox's paper was the first one, and his big insight was to start an inductive approach to the conjecture. So he was able to use an inductive proof to show that if you could prove the conjecture for all the finite simple groups, then you can get the conjecture in full from that. And also Wilcox proved the conjecture for many different finite simple groups. So he actually established the conjecture for all the infinite families of simple groups and also for some of the sporadic ones. So that left a couple of the sporadic ones where the proof was completed by Evans and by Bray, and they used tools from computational group theory. So there was some computing going on there. So we know now this is now a theorem of Wilcox, Evans, and Bray, and we know it's true. Somewhat excitingly, about 6 years ago, an alternative proof of the conjecture appeared in a paper by Eberhard, Manners, and Mrazović, which used basically completely different tools from the first proof. So it used techniques from analytic number theory. Specifically, their main tool was non-abelian Fourier analysis. So the new proof had one disadvantage, that it only worked for sufficiently large groups, so it didn't get a proof for all groups like the original proof worked. But it also had one advantage, that it didn't rely on the classification of finite simple groups. And finally, the new proof, it also proved a more general result than the original one. Specifically, it showed not just, so under this Hall-Paige condition, it showed not just that there exists one transversal, but they actually obtained a very precise count on how many transversals every group has. Okay, now starting point with Alp was to try and come up with a third proof of this conjecture using a third set of methods. And we wanted to generalize the conjecture in a different direction. So next I'll tell you about the direction in which we wanted to generalize this conjecture. So we were interested, with a view for some very specific applications, in not looking for transversals in just full groups, but also their subsquares. So let me illustrate what I mean by that. So here you have a multiplication table of Z6, where the group operation is addition. And let's look at a subsquare. So by subsquare, I mean you take some number of rows, a set R of rows, a set C of columns, and a set S of symbols, where they all have the same size. So as an example, let's use the set of rows 1, 2, a set of columns 2, 3, and let's use the set of symbols 3, 5. So this means that I'm looking for a transversal using these two rows, using these two columns. So that's C, that's R, and using the symbols 3, 5. So you want to just look at this subsquare and find a transversal there using just the symbols that I'm allowing you, namely 3 and 5. So in this case, it's possible to find one, right? So here's a transversal using the symbols I gave you. And basically, we want to understand as well as possible for which R, C, and S you can get a transversal. Let's try and emulate the strategy that Hall-Paige had to this problem. So can we come up with some natural necessary condition? And that's not too hard. So here is the natural generalization of the condition in the Hall-Paige conjecture. So I'm going to call this the generalized Hall-Paige condition. And the condition is that if you multiply all the elements of R, multiply that all the elements of S, and of C, and multiply that all by the elements of S inverted, you end up in this commutator subgroup. So let's look at the example of this with the R, C, and S I gave you. So multiply all the elements of R. So since the operation addition, that means 1 plus 2. All the elements of C, that means 2 plus 3. And you subtract all the elements of S, that's 3 and 3 plus 5, like this. So you end up with getting 0. So 1 plus 2 is 3, 3 plus 2 plus 3 is 5. So the first two terms give you 8, and then you're subtracting 8 again, so you get 0. Okay, and 0 is the commutator subgroup of an abelian group. So this condition holds in the example I'm giving. And indeed, there is a transversal there. Now, could this necessary condition be actually sufficient for getting a transversal? It's not hard to see that the answer is no. So this necessary condition is not sufficient if you're in this subsquare setting. So let me modify the example we have a little bit to show you that it's insufficient. So what if instead of 3 and 5, I instead gave you the symbols 0 and 2? Then the condition still holds, because 0 plus 2 is congruent to 8 mod Cichacz as well. But I mean, you definitely can't get a transversal using 0 and 2 in the subscript, in the subsquare I'm giving you, this subsquare, because 0 and 2 don't even come up once in that subsquare. So you clearly need something stronger than what I'm telling you. And the idea we had with Alp was that we generalized the conjecture not to arbitrary subsquares, not to arbitrary RCNS that I'm giving you at this slide, but rather to RCNS, which are close to being random in some sense. So next, I'll explain to you what close to being random means and state to you our main theorem. So this is the main theorem. So let me go through it nice and slowly. So the setting is just like in the previous slides, you're in a multiplication table. So this is a multiplication table of a potentially non-abelian group. And then we have three random subsets, RCNS. So R, C, and S are, R is a set of rows. So maybe it's these rows. C is a set of columns. Together, they give you some kind of subsquare. And also there's some set of symbols which I want to build a transversal using. So RCNS, they're random sets, meaning that for every group element, you put it into R with probability P, into C with probability P, and to S with probability P, and you make every single choice independently of each other. So this will give you three sets of size roughly Pn. Okay, so we're not going to actually look for a transversal in RCNS because RCNS are really unlikely to have a transversal. So if you think about it, although they in expectation have the same size, actually they're very unlikely to have exactly the same size. So there'll be some deviation from the expectation. So if they're not going to have the same size, you're not going to have a transversal there. And moreover, this extra Hall-Paige condition is also very unlikely to happen if you just have a random RCNS. So we're not going to show that RCNS have a transversal. Instead, we show that if you have such an RCNS, then with high probability, they have a certain property. The property is that for every single other set, R prime, C prime, and S prime, where this R prime, C prime, and S prime, they're like a small perturbation of RCNS. So R primed is some set like this. 1 second. Here we go. So R prime is like it has it's a set which is close to R in symmetric difference. C prime is a set which is close to C in symmetric difference. So C prime looks something like this. And S prime is a set which is close to S in symmetric difference. So we have three sets like this, and this gives you a subsquare which is close to the random one you started with, but not exactly equal to the random one. And what we showed is that for such subsquares, so ones which are close to the random one, there the two necessary conditions are also sufficient. So for R prime, C prime, and S prime, as long as they have exactly the same size, and also as long as they have the same size, and as long as they satisfy this Hall-Paige condition, then they have a transversal. So this is the theorem we ended up proving. And I'll now go on to the reasons we were proving it in the first place, which is applications to various problems in group theory. And towards the end, I'll also say a little bit about the proof of this theorem. So the very first application.
Can I ask a question?
Yeah.
So if you don't pick random, you just pick a set of columns, you take the set of rows arbitrarily, but with the same size. Can you make sure you can always find a set of group elements to have a transversal? Like you choose R, you choose C, but you don't choose S.
Oh, that's really great question. So that's actually an application I will talk about. Yeah, so in 2 slides exactly, I will talk about this question.
Okay, thank you.
Yeah, that's an excellent question. That was like the first motivation we had for actually proving this. Okay, so but just before saying that, like the sort of even the application before that is, can we from this theorem deduce the Hall-Paige conjecture itself? And the answer is yes. You can. This theorem is the generalization of the Hall-Paige conjecture for sufficiently large groups. The way you see that is if you set this probability. So if you set the probability equal to 1, then it ends up being something stronger than the Hall-Paige conjecture, which is this. So if you set the probability equal to 1, then the random sets you have here just end up being the whole group because it's with probability 1. And the theorem simplifies a bit. So it ends up saying that for a sufficiently large group, as long as you have 3 subsets which satisfy the 2 kind of necessary condition, namely they have the same size, and that size is large, and also they satisfy the generalized Hall-Paige condition, then they have a transversal. And the converse of this theorem is also true. So if you're talking about only sets which are of this size, then they can have a transversal if and only if they satisfy these 2 conditions. So this, of course, generalizes the Hall-Paige conjecture for large enough groups, because you can take R prime, C prime, and S prime to be equal to the whole group, but also goes a bit further than the conjecture, because it applies not when R prime, C prime, and S prime can be a bit smaller than the whole group. So in a way, this is kind of like a stability version of the conjecture. It shows that as long as you're close to being the whole group, then the only thing that can stop you from having a transversal is exactly what stops the whole group from having a transversal. Because that's kind of the very first application. Now let me go on to the question that was asked, which is the question of, as I understood it, is if you specify sets of rows and columns, but you don't specify which symbols you're allowed to use, is there a transversal then? So this was actually a conjecture of Snevily. So you're given a set of rows and you're given a set of columns, but you're not given a set of symbols. So the rows, let me use an example. So let's use the set of rows 1 and 4. And let me use a set of columns 0 and 3. So I want you to find a transversal in the subsquare. And Snevily, he doesn't care about what symbols you use. You can use any symbols that come up in that subsquare. So let's look at 1 and 4. So that's not it. 1 and 4 is this row and this row, and 0 and 3 is this column and this column. So you want to find a transversal used inside these 4 entries. Okay. And Snevily was interested in just cyclic groups. So we're like not talking about anything non-abelian in this bit. So we're just looking at cyclic groups. And Snevily was wondering when you have a transversal there. And he made a conjecture about what the answer should be. He conjectured that you always have a transversal in a subsquare of a cyclic group, with just one exception. So, and that exception is what I've given to you in this example. So in this example, there isn't a transversal. So if you look at the 4 entries there, you're not going to get a transversal. And there isn't a transversal for kind of a silly reason, that the subsquare we get here. So if you just look at the 4 entries I've given and forget about everything else, well, it's just exactly the same as the multiplication table, the 2x2 multiplication table we had on the first slide, which didn't have a transversal. And Snevily conjectured is that the only way that a subsquare of a multiplication table cannot have a transversal is if it's isomorphic to a full multiplication table of some cyclic group which doesn't have its transversal itself. And this was our first application. So let me tell you first about what was known about Snevily's conjecture. So it was known, so a lot was known for groups of odd order. So here, the first result was by Noga Alon, who proved the result for all cyclic groups of prime order. So for them, he showed that for odd primes, you always have a transversal, as the conjecture predicts. And the technique used for this was an early application of the combinatorial null-Schoenstatt. So this was extended by Dasgupta, Karolyi, Serra, and Szegedy, who extended the proof to work for all odd-order cyclic groups. And then Arsovsky extended this even beyond cyclic groups by showing that all odd-order abelian groups, their multiplication tables, always have transversals. So for odd-order groups, we really have a good understanding. And for them, you always do have a transversal in all subsquares. So this kind of weird exception doesn't come up in odd-order groups. So our theorem, it can be used to prove the conjecture for sufficiently large subsquares. So basically when these R and C are large enough, to prove the conjecture in general, and actually can go quite a bit beyond the conjecture to prove the following theorem, which generalizes the conjecture to all groups. So whether you have an abelian or non-abelian group, if you have a large subsets of any group, we can characterize exactly when you have a transversal and when you don't. So I won't really go through it in too much detail, but basically there's two exceptions. There's two reasons why a subsquare of a group might not have a transversal. The first of these is the natural generalization of this condition that Snevily came up with. So basically it's saying that a subsquare of a group might not have a transversal if that subsquare is isomorphic to a full multiplication table, which doesn't have a transversal. The second condition is a different kind of exception, which doesn't come up in cyclic groups. So in general groups, there's another thing that can go wrong. So this is kind of our first application. And the proof of this theorem, it's not too hard using this p=1 case of the Hall-Paige this random Hall-Paige conjecture that I talked about. So once you have this theorem, so this theorem is in a way stronger than what Snevily was asking, because this theorem lets you prescribe R and C, so the rows and columns, and also the symbols, whereas Snevily didn't care about the symbols. So it's maybe not too surprising that if you choose the symbols carefully in this theorem, you immediately will get Snevily's conjecture. Okay, so that's the first application. Let me now list a couple more applications in less detail, just to give you a sense for the kind of things you can prove using our theorem. So here are three more applications. All three of them basically say you're given a group as an input, and you're trying to find some kind of structure in the group, which in this case now is not a transversal anymore. Okay, so the first conjecture by Keedwall asks you to find an ordering of the group. Let me give an example of what Keedwall is asking. So he's given a group, so let's use the group Z4 as an example. So let's order the elements of Z4, 0, 1, 2, and 3. Okay, when you've ordered the group like this, you can work out the partial products, or in Z4 partial sums, because the operation of addition. So the first partial sum is just 0 by itself. The second one is 0 plus 1. The third one 0 plus 1 plus 2. And the last one 0 plus 1 plus 2 plus 3. Let's work these out. The first one is 0. The second one is 1. This third one is 3. The fourth one is 6. So that's 2. And notice that the partial sums we got with this ordering ended up all being distinct. So Keedwall, he defined a group which you could order like that as he called it a sequenceable groups. You can order it such that all the partial sums are distinct. And he asked for which groups are sequenceable. He made a conjecture about which ones are. So basically there's an infinite family of abelian groups which are not sequenceable. And then there's also 3 sporadic exceptions, D6, D8, and Q8. And using our techniques, we can prove this is true for sufficiently large groups, so where the only exception is this infinite family of abelian groups. Okay, so that's one application. Another one is a problem of Evans, also about ordering groups, where I'll illustrate this with Z7. So we can order Z7 like this. So let's again use a kind of simple ordering: 0, 1, 2, 3, 4, 5, 6. And now what we're going to do, what Evan does is he, rather than looking at like the partial sums like Keedwall, he looks at sums of consecutive elements. So 0 plus 1 is 1, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 4 is 7, that's 1 and 1, oh, sorry, that's 0 mod 7. 4 plus 5 is 9, that's 2 mod 7. 5 plus 6 is 11, that's 4 mod 7. And also imagine this is lying in a cycle, so then 0 plus 6 ends up being 6 mod 7. And notice that the sums of the consecutive elements we got here all ended up being distinct. So Evans called a group where you can order it like this harmonious, and he asked which groups are harmonious. So this is also a question which we can answer. And finally, a problem of Tannenbaum, which I will also illustrate with Z7, where Tannenbaum asked for particular partitions of groups. So Z7, you can partition it into 3 sets like this. We'll put the identity by itself. We'll put 1 and 6 together, and we'll put the remaining elements 2, 3, 4, and 5 together. So that's a partition of Z7. And notice that if you add up the sets in each of the subsets I gave you, you get 0, 2, 3, 4, and 5 end up to 14, which is 0 mod 7. So this is called the zero-sum partition of the group. And Tannenbaum was wondering for what kind of sizes of sets you can get a zero-size partition. So in this example, you have one set of size 1, one set of size 2, and one set of size 4. And Tannenbaum was interested for all abelian groups, what kind of sizes you can get. And this is, again, something we can characterize fully using our techniques. So this hopefully shows you that there's kind of a wide range of different problems for which you can use combinatorial methods in group theory. And I'd like to use the last few minutes to tell you a bit about the proof of sort of the main result I told you about. So I'm going to focus on this.
So maybe one question, if you can
go
back. So some of these things, can be phrased in terms of finding rainbow objects in some colorings, like a problem of Evans. If you take, for example, at least your abelian group, then you're trying to find, say, Hamilton cycles, which is rainbow, right? Something like that.
Absolutely, that's an excellent question. So, and that's exactly how we actually think of these problems, and we write their proofs. So Evans, so maybe just since you asked, so Evans, so if we look at, say, let's look at the example of Z4. So the elements 0, 1, 2, 3. If you construct a coloring of K4, where you color the edges based on the sums modulo 4, so this one gets the color 1, this one gets the color 3, this one gets the color 5, so that's 1, this one gets the color 3, and these ones get the color 2. So you get a coloring of the complete graph, and Evans' question can be rephrased as saying you're looking for a Hamilton cycle in this graph where all the colors, sorry, this one's 0, not 2, where all the colors are different. Actually, Keedwall's question can also be phrased like this, although you need to do like some tricks to make it look like this. So Keedwall's question, you can phrase it ends up being equivalent to a directed version of Evans's question, where you have a directed complete graph where you color the edges by the differences rather than by the sums. So so if this is 0, 1, 2, 3, then so 1 minus 2 modulo 4, so that's minus 1, so that's going to be 3 modulo 4. Whereas 2 minus 1, that's going to be 1 modulo 4. And this way you get a direct complete graph, and finding a Hamilton path there ends up being equivalent to Keedwall's conjecture. Tannenbaum's problem, I don't think has a phrasing in this flavor, so it's a bit different. That's a good question. So that's exactly how we think about this.
Okay.
Okay. Let me tell you a little bit about the proof. So I'm going to focus on this p=1 case. So this is basically what was phrased a couple of slides ago. The only thing I changed here is I changed the error term to just be a slightly nicer number. So we want to find a transversal here. So to make things a little bit simpler, I'm going to just look at a specific group. So look at the group Zn, the cyclic group. This is already quite interesting because for this group, you get the Snevily conjecture, which Snevily was asking about. So even this case is quite interesting. And if you're in an abelian group, this generalized Hall-Paige condition ends up simplifying. So this turns into saying that the sum of R prime plus the sum of C prime minus the sum of S prime is equal to 0. So basically, the theorem ends up looking like this. I'm going to change it a little bit again. So I'm going to replace S by minus S. So basically, minus S means you just change every element to inside S to minus itself. The effect that this will have is that instead of this minus, you'll have a plus. And instead of looking for an S transversal to transversal using the symbols in S, you look at the transversal using the symbols in minus S. And the reason this will make the theorem a bit simpler is this condition is now kind of symmetric in R, C, and S, which will just make the notation a lot nicer later on. So the theorem becomes this. So this is all still equivalent to this p=1 case of the theorem. Okay, so now how do we try and prove this? So the proof uses something called an absorption strategy, which has been like a really influential technique in combinatorics for the last 15, 20 years. And the main difference in our version of the absorption strategy to other ones is that in our theorem, you have this algebraic structure. So you need to get the absorption strategy to work in like a group theoretic setting. So we're not the only ones who've ever done this. So in particular, the recent solution to the n-queens problem by Keedwall and Votel also works by using an absorption strategy in the presence of an algebraic structure. And there's some interesting parallels between our proof and their proof. Okay, so what do I mean by an absorption strategy? This basically just means a strategy which has two ingredients, so kind of two main lemmas, one which is some kind of approximate solution to the problem, and the second one which is an absorption lemma which turns the approximate solution to an exact one. So first, to say a few words about the approximate solution of a problem, what does that mean? That means you have some lemma which has exactly the same assumptions as the theorem, but you should replace the conclusion by something that's a little bit weaker than the current conclusion. So here it is. So the assumptions are exactly the same. The conclusion, rather than asking for a transversal, you look for a partial transversal, which is quite large, but not completely large. So this means that you want this many symbols which don't repeat rows or columns. Let me explain why this is true, and I'm going to use like some tools from hypergraph matchings to do this. This means we first build some kind of auxiliary hypergraph. So the auxiliary hypergraph will be tripartite, so it'll have three sets. The vertex set will be partitioned into three sets, which are just R, C, and S, their union. And it'll be three uniform, so you'll have edges like this, which have one vertex in every part. When do we have an edge like this? We have an edge like this whenever the three things add up to 0. So in this language, the theorem we're trying to prove, so the theorem at the last slide, it's the same as saying that this hypergraph has a perfect hypergraph matching. Whereas this approximate version is saying that this hypergraph should have a large matching. So why might this hypergraph have a large matching? So to figure this out, we're going to ask the question, what is the degree of every vertex in this hypergraph? So let's, for example, zoom in on this vertex R and ask for what its degree is, how many edges is it contained in. So let's first answer this question in the case when RC and S, rather than just being large, let's say that RC and S is the whole group. So when you're not in the subsquare, you're in the whole group. So then it's very easy to see what the degree of the vertices are. So this ends up just being the number of solutions, because of how the edges are contained, solutions to the equation R plus C plus S is equal to 0. So just by the definition of the edges. So in this equation, so this guy R, that's fixed, right? Because we're looking through a fixed vertex, whereas C and S are variables. And you can like exactly count the number of solutions to this. Basically, once you've picked C, S is determined, so the number of solutions is exactly n if R, C, and S are the whole group. If R, C, and S are not the whole group, then you're going to have a small error. So if R, C, and S are just this big, you're going to know the degree is not exactly n, but you're going to have an error which is like proportional to how big the degrees are, or how big R, C, and S are. And to this, so this is a hypergraph, which is nearly irregular, so you can use like the well-known Pipin-Spencer theorem, which says that nearly irregular hypergraphs have a hypergraph matching which almost covers everything. So that gives you this approximate version. So that's quite standard, and the main kind of new ideas are for dealing with the remainder of this many vertices which are not covered by this matching. Let's think about what properties this remainder have. So let's let Z equal to the remainder. So the stuff that's not covered by the matching from the previous line. So first of all, the remainder has the same number of vertices in R, C, and S. So this happens because R, C, and S have the same size because of this bullet point, and also you took out a matching which has one vertex in each edge of the matching has one vertex in each of R, C, and S. So therefore, you get that these three sets have the same size, and you also know what size they have. They're exactly this number. Okay, that's the first property that Z has. Z also has an algebraic property. So the remainder has the property that if you add up all the elements in the remainder, you do the like addition in the group you're sitting in, you're always going to get 0. Why does this happen? So it happens first of all because R, C, and S have the property that when you add them up, you get 0, and also the edges in the hypergraph matching, by the definition of the hypergraph, each edge adds up to 0. So you're kind of the remainder also has to add up to 0. So basically, we need to come up with some kind of absorption lemma, which can construct matchings with set Z, which satisfy these two properties. Okay, so let me now tell you what a lemma like this looks like. So I'll use one definition for this, a definition of a set absorbing some collection of sets. So we say that a set A, think of this as a set like this. This is in the vertex set of this hypergraph we defined. It absorbs some family of sets, Z1, Z2, and so on, where you think of the set Z being disjoint from A, but not disjoint from each other necessarily. So A absorbs these sets if for any one of the Zs, together with A, you can cover this by hyperedges in the hypergraph we're considering. So you can somehow cover the union of A together with each Z by a perfect matching. Okay, and the lemma which we prove, so this is kind of the main absorption lemma, is that if you have any set, so there exists a set in the hypergraph which isn't too big, which absorbs the formal length family of sets, and that family is exactly the sets that the remainder satisfied a couple of slides ago. So it's the sets Z, which add up to 0 and have the property that they have the same number of elements in each of R, C, and S, which is, I should say, 4 times n to the 2/3. Okay, I won't exactly explain how to combine this with the approximate version, but it takes a little bit of work. So, but basically the strategy is first you apply this absorption lemma, you get your set A, then you apply something like Pippinger's tensor to the remainder to cover most of the remainder by hypergraph matching, and then you use the definition of absorption to cover A together with the remainder using a perfect matching. So it takes a bit more work than I'm showing you here to get the numbers to work out, but it's possible to do. So for the remaining time, I'll just tell you about how to prove an absorption lemma like this, which is that's kind of the main new ideas of the proof. So here it is again. The way I think about getting to a lemma like this is to first prove some weaker versions of it and then build up slowly to a lemma like this. So this lemma says that you can absorb some large family of sets. So let's first prove a lemma which can absorb some smaller family of sets. So actually one remark which I didn't make before is, so one big difference between this absorption lemma and previous ones which I've used in literature is that the sets you can absorb here have the property that they have to have some kind of algebraic structure to them. This is necessary. So if you go back here, so if you have a set A which absorbs some family of set Z, so we know that say A together with Z2 has a perfect matching. That means that if you add up all the elements of A and you add up all the elements of Z2, you're going to cover this by a perfect matching, which means that this sum has to be equal to 0, because the only way you can cover a set by perfect matching is if its elements add up to 0. But similarly, A together with Z1 has to add up with 0, and from these two equations you get that Z2 and Z1 have to have the same sum. So basically, if you want to prove an absorption lemma for the hypergraph which we're looking at, you need some algebraic condition like this. So let's keep this algebraic condition, but try and prove this lemma with the second condition where we talk about the sizes of the sets we're absorbing weakened significantly. So first I'll weaken it to this. So the weakening will be that I'm just going to ask that the sets which I absorb, they're zero sum. They have 2 elements in R, but they have no elements in C and S. So basically, if this is R, C, and S, I'm only absorbing sets like this. Let me go a little bit further even and say that I'm just going to get a set which absorbs one of 2 sets. So you either absorbs this subset of R or this subset of R. So to again draw you the picture, so here's R, here's C, here's S. Inside R, I have the elements 1, -1, 2, and -2. And I need to construct with some set A which absorbs those 2 sets. So A will look like this. It's going to have 4 elements, X, Y, Z, W. So this is what A will look like. It'll have exactly 4 elements. So let's see if we can get 4 elements which absorb the 2 sets we want. So first of all, we want A to absorb 1 - 1, which means that A together with 1 - 1 should be coverable by a perfect matching. This means so let me wait, how much time do you have? Yeah, I should stop soon. So let me just finish this very quickly. So I need A together with 1 - 1 to be coverable by a perfect matching. Which you can do by, say, getting these 2 green things I've drawn to be hyperedges of your graph. Also, I need A together with 2 - 2 to be coverable by a perfect matching, which you can do if you get this thing and this thing to be hyperedges in your graph. So to write down what we want, we need elements X, Y, Z, W, which are distinct which satisfying 4 equations. So the first equation is that the 4 things in this green oval add up to 0. So x plus z minus 1 is equal to 0. Then you also need y plus w plus 1 is equal to 0. You also need z plus y plus 2 is equal to 0. And you need x plus w minus 2 is equal to 0. So can we get such x, y, z, and w? So there's 4 equations here. And there's 4 unknowns, which actually doesn't look very promising, because if there's 4 equations, 4 unknowns, you usually will only have 1 solution. But actually one nice thing happens here is that one of the equations is redundant. You can see that by seeing that if you add up these 2 and these 2, you get the same thing. So that tells you there's lots of solutions to these equations. So there's n solutions, which is basically what you want. So you get lots of solutions. You can also get by counting that some of them are distinct. And that's the end of the proof of this lemma. To get the full absorption lemma, you kind of start with this lemma, then you gradually build up stronger exhaustion lemmas until you get the one we wanted. So let me maybe finish with one open problem, which is this. So this is exactly the p equals to 1 case of the main theorem I showed you. And we saw that if you have sets R, C, and S, which have the same size and which are large, where this alpha n is really close to being equal to n, then you always have a transversal. And my question is, how large do R, C, and S need to be? So we can prove this when R, C, and S are like 0.999999 n, but we don't really know what the right value should be. So let me stop there.
Okay, so thank Alexey for the really nice talk. Questions? I have a question exactly about this open problem.
Yeah.
It's a bit similar in the spirit. I was a bit interested in like completion of Latin square. So there is some similar question there. So what is the lower bound for this alpha you're getting? Can you get some substantial thing? In particular, 10%, 20%, quarter.
Yeah, no, I think it's more than that. Like you can get, I don't remember their exact constructions. So I think you get something like more than a half, but I don't know if I can come up with. There's some kind of algebraic construction. So like, I don't know, you take R, let's see if we can come up with C. Say R is all the even numbers, C is all the even numbers, S is all the odd numbers. That gives you a half, doesn't it? I think there's probably something even better than this, but yeah,
Right.
I don't have a good guess. I don't have a conjecture for what the right value should be now.
Okay. Yeah. More questions? See. Okay, so very nice. So really, indeed, very interesting methods. So actually, one more question. So when you say that it works only for very large things, so just your intuition. So the proofs which you have versus this proofs which you originally mentioned by number theory guys. So where n is larger, right? So what or they are roughly the same. So this doesn't need to make n very huge, right? It's just basically whereas concentration inequality should work, right? Which means n would be maybe in, I don't know, thousands, right? Or
yeah. So you're talking about these guys, Eberhard, Manners, and Mrazović, yeah?
Yeah.
Yeah, it's hard to. So I think if you just read off the 2 proofs there, theirs gives it probably a better bound.
I see.
Because they somewhat at least tried to optimize things. We didn't really try, and we don't use any like really high power to click greens like graph regularity, so there aren't any tower type estimates. But equally, it's quite a long technical proof, so it's hard to actually optimize things.
Can I ask a question?
Yeah.
So is this subgroup which you denoted as a COMG a very obvious choice, or like because you only use that two properties, can you have to choose some other alternatives of this?
What do you mean? So instead of this condition, can I change it to something else, or?
Like you just used the property of this subgroup to be normal, and then abelian if you modulo this subgroup. Can you choose some other definitions of subgroups with some other properties? No.
So can you? What do you mean by choose? Do you want to replace this condition by something else, or
maybe
do you want?
I'm just asking. Maybe you can replace this subgroup by some other subgroups with the same two properties.
Okay, so one thing is that the commutator of G is, you could define it as the smallest subgroup of G.
Such a factor is
Such that the factors would be in. And smallest, not even just by size, but also containment. So whenever you have a subgroup H, such that G over H is abelian, H contains the commutator of G. So you could replace it, but you could find another H which has the property, but somehow it will contain the commutator subgroup of G. It's kind of a less strong condition in that way. That's a good question.
More questions? Okay, so great. So thank Alexey again for the beautiful talk and very nice results. And thank you everybody for coming. So as I said, this is our last seminar this semester. And so I hope to see you all next year. So thank you, Alexey. We can stop recording.